this signal processing block is a interesting block, and lot of learning has to happen, training and testing has to happen in the signal processing block. So it is good to know before you actually see a demonstration what actually happens inside the signal processing block. Okay. So essentially when you talk about signal processing, you talk of these two terms. In any learning that you will come across in future, whether it is simple statistical models or neural network models or whatever, you will come across these two terms. One is the training and the other is the testing. So when you say training, you are essentially creating the model. So it's all about model generation. Okay. And when you say testing, you talk about pattern matching. So this is the most important thing. We stopped this in the previous part, so I am just speaking from here, is indeed that you have signal processing divided into two parts. One is the model generation and the other is the which includes the training part, and the other which includes the testing part, which is essentially the pattern matching part. Okay. Now whenever we talk, okay, what is actually happening, we should know that a little bit in detail. Here I have put down what exactly we are talking about in terms of this model. This is about the model. Okay. This is the model. Speech essentially is nothing but sequence of phonemes, right. You have a sequence of phonemes, you want to encode them as sequence of words, essentially you encode them in sequence of words, and then you will be able to put these words with certain probabilities. You will be able to estimate how these word sequences occur, sequence of words occur, and then you will end up with a sentence. So sentence comprising of words and each word comprising of several phonemes. Okay. And phonemes itself will have multiple states. You can have a start, you can have a sort of a peak state, and you can have a end state. All of that can also be visualized from the spectrogram that I showed you, how you can have multiple states within a phoneme. So the acoustic manifestation of banana, we took that as an example. I can be talking in a very nice pleasant way and say, here is a banana, I can say, right, when I am very happy. But if I am really aggressive and I have some mood problem and all that, I will say here is a banana, right. You actually mean the same word banana. So the way you pronounce, the way you do things, all depends on the position of your jaw, the position of your tongue, the position of your lip. All these, each one of us have different manifestations of our own physical systems. So all of this, including the emotional state of the speaker, all of this has to be considered before you actually say anything about the word. So here is the problem. Supposing you take, I mentioned to you about the phonemes, right, 24 consonants and 20 vowel based. I mentioned this already. Take one specific example, okay, of this phoneme okay, I. So the question is, when somebody said or I, what did he or she say, right? Who actually, what is the actual utterance? Is it this or that? So to decide that, the computer system actually looks at the probabilities. The probability of given a set of observations, if it is greater than the probability of I given the set of observations, you say that indeed the utterance is this or the utterance is that. Okay. So this is, I am just looking at the phoneme level. Now how do you get to this probability? You get to this probability by finding out the density function, probability density function, okay. And these density functions are parameterized, these are parameterized models. You say parameterized by theta a and parameterized by I, which is theta I. Now how do you parameterize, what is this theta? Theta is nothing but the fact that the density function is a mixture of Gaussian models, is nothing but a mixture of Gaussian. See, the problem with Gaussian, there is a limitation on what Gaussian can do, and why we choose Gaussian mixtures. The problem with the Gaussian is that if you take a simple Gaussian, it is not very useful. Okay. So, essentially GMMs are very good for the, so let me go to the next sheet. GMMs essentially are universal approximators. So, I will call them GMM as a universal approximators of densities. Okay. If you look up Gaussian PDF, you should be able to put down the Gaussian PDF, that is a very well known expression. So, you can put down that. Essentially theta, when we say, when I wrote there theta, I actually mean mu and sigma square. Okay. Mu is the mean, and what is sigma square? Sigma square is the variance. Okay. So, essentially you have to parameterize, that is the, so the whole model is a parameterized model. When you want to estimate these probabilities, you have to go in for a you do it with the probability density function, and you typically use Gaussian mixture models for the purpose of the estimation of these probabilities. So, how do you model this phoneme? That is the next question. It is all good to say that a phoneme should be modeled as a let us say a density function and all of that, and particularly as a probability density function of a Gaussian mixture model and all that. Why is this Gaussian mixture at all coming in the first place? So, let me tell you, let me explain with you with a very simple example. Take this phoneme that we mentioned, this a, right, you take this phoneme a, right. If you take that, you can model this phoneme in 3 phases. Okay. You can be talking of entering that phoneme, that means it is transiting from another phoneme somewhere. So, transition from a previous phoneme, you can have one density function 1, you are remaining in that phoneme means it is in a steady state, that is another density function 2, then you are transiting to the next phoneme, that can be another density function which is 3. Okay. Now, this is not going to be sufficient, you also need to know the time duration of these intervals, and then and therefore you need to arrive at the transition probabilities. This whole system has to happen in real time as you are talking, right. Therefore, estimating these parameters in real time is normally done using algorithms. You need another algorithm to do that, and that algorithm, which is a very important thing indeed, is the expectation maximization algorithm. Okay. Let me put that down, expectation maximization algorithm. Okay. EM algorithm, it is called EM algorithm. Okay. Now, it is nothing but an iterative scheme for learning, it is a iterative scheme for learning parameters. This is what you are interested in. You have to learn the iteratively, you have to learn iterative learning. So, algorithm, let me ensure that I show you this, learning parameters in mixture models, Okay. So, essentially this is a hit and miss kind of a system. You start somewhere and then you end up with the model parameters. So, what you do is first step in this is called expectation maximization. You choose some initial values, and then you do what is known as a E step. This E step is nothing but evaluate the posterior probabilities of data points. You evaluate posterior probabilities of a data point, of some point of it. I will just give as an example of some of the data point which belongs to the mixture component. Okay. Then what you do a M step, that is why it is called EM. What you do is, since you have chosen some initial values, you have to go and update, you go back and do an update to re-estimate, update responsibilities, I will call it responsibilities to re-estimate the parameters. You go on doing this step by step till you are able to match the exact PDF, okay, the density function, which looks very similar to the original. That is, when you spoke, you got something, the utterance is related to something which you only have seen, you have only observed that, and somehow you are trying to fit that observation back into the model, applying these parameters into the model, into the GMM model, and then getting back the original as close as possible to the original. Then you say that the model has converged and you have actually found out the probability density function of the PDF of, you have estimated the model parameters essentially, which can generate the PDF essentially, that is what it means. So, this theta, so all after you do all this EM's algorithms and all that, you will end up with your objective. What was your objective? To get the model parameters of this the GMM, parameters of the GMM essentially, which uses maximum likelihood estimate methods to estimate the. So, you will use maximum likelihood estimates of model parameters of theta, okay, you will be doing that. So, essentially you may also end up in a, sometimes when you see the demo, you will also end up with a certain way of doing it using maximum a posteriori, it is called MAP, a posteriori, okay, it is also called MAP adaptation. Okay, I will give you a feel for this, then we will go and see what all you can do with this. See, it is like this, right? You have speaker independent, model, okay. You have a speaker independent model, you want to adapt this speaker independent model to a given speaker, adapt it to a given speaker. This is the key. So, they use this technique of MAP, maximum a posteriori adaptation, in order to do that. Now, question is, where is it useful? Why is it useful? Why are we discussing this? Because the demonstrations that you see can actually, you can do MAP adaptation, okay. So, for example, why is it useful? It is useful because let us say it was difficult for you, it was difficult for one to get sufficient number of examples for robust estimation of parameters. Okay. But what do you have with you is you have access, but I will say but you have access to large number of similar, this is important, similar examples which can be utilized. So, many acoustic applications, speech to text applications, actually you can do map adaptation also. Okay. So, you can see all of this involves intricate math, and it mostly uses the Bayesian techniques, estimations. So, I strongly urge that I have not covered too much of math here. I want you to go and read a little bit of background, so that you will be able to understand what exactly is happening. You could connect easily once you know the math a little bit better. Alright. So, but however, this is already sufficient for you. I hope you got a feel of how a phoneme essentially is modeled before it arrives at it. There is a phoneme, there are states in the phoneme, there are essentially you are looking at parameter estimations of that phoneme. We mentioned about the 3 states which I wrote it here. So, transition from previous phoneme, then you have a steady state, you have a transition to the next phoneme. All 3 of them can be modeled as density functions. You have multiple density functions 1, 2 and 3 in this case. You also have time durations, and all of it falling into the GMM HMM model, and the whole exercise is to estimate the model parameters. Estimation of model parameters is done using expectation maximization algorithm, and you arrive at the closest match to what was spoken, whatever was uttered. So, that is the goal. Now, let us move on to see some demonstrations of what is possible and how you can actually build your own application to do this. Let us start with a small demonstration. Payal and Rahul have put this demonstration together and have done a wonderful job to give you a feel of the problem. What you can do is, if you have an Android phone, go to Google Play, okay, and download an app called CMU Pocket Springs. It is written here. Go and download CMU Pocket Springs. This essentially uses all that we spoke about in the, it uses the GMM HMM model to recognize the speech. It takes the phoneme, splits it into 3 parts. I will just recap quickly. Into 3 parts, the transition, steady, and then going on to the next stage, right. All the 3 parts it is done, it uses the transition probabilities, builds the model, you have to estimate the model parameters, all of that it does. So, you can start by recognizing speech in that Google Play model by uttering the word "Oh mighty computer." You should use this word. See, everything in speech to text processing is all about alignments. This can be a nightmare for you. It is all about alignments. If you do not align properly, because speech is a time, it is a time series, right. You will be taking, it will be, the system will be taking samples of 10 milliseconds and start to decode the phonemes, the words from, so if you say, so sentence, words, and from within the word the different phonemes which make up the words. So, all of this will have to do, you have to start somewhere, some index has to be there. So, that is essentially related to the alignment. So, this alignment, time alignment is an important thing. Once you, so this almighty computer is like you start and then you say whatever you have to, it is expected to decode. So, please note, in any implementation this alignment can be a very important problem for you. So, if you do that you will see something, do not worry about it. What we have done in the lab is we have created a very simple example for this course is related to airplanes and passengers sitting in an airplane. For example, if there is a cabin announcement by the flight attendant, for your safety please remain seated, supposing it is said like that, particularly when there is turbulence, the flight attendants keep announcing that you should remain seated in your seat. That is something that you hear and you may want to sort of convert it into some sort of textual form. I mentioned to you right in the beginning that speech to text has various applications, particularly for persons with different abilities. So, that is the reason why this example is extremely important. What we have done is we have trained the language model, essentially a set of sentences which essentially it is sentences whose occurrences are based on probabilities of words, right. That is essentially the language model. You are talking about occurrences of words and their probabilities of in the sequence in which they can occur, essentially related to the language model. Then dictionary is essentially all those words which comprise of the sentences that you can form. So, you have a dictionary model, you have the language model, and all of that from a corpus of everything related to flight. Okay, only flight corpus is included here. So, you create all the acoustic models, you create all the language models specific to the in-flight system. Let us see if you do such a let us say a fine adjustment, then what would happen if you use words which are specific to airplanes, what would happen if you use words which are away from an airplane scenario. So, we will try 1 and followed it up by 2. Okay. So, if I have trained this system to work for 1, anything related to 2 should not be decoded properly, because the language model, the dictionary and the corpus that was used to train the models were all specific to the in-flight data. Okay. So, let us turn our attention to this mobile phone app downloaded from Google Play called the CMM Pocket Sphinx, modified by our project associates in the lab to support 2 buttons, one is called start, the other is called stop. Okay. So, I hope you can see that here. Okay. Now, I will turn it round, I will press start and I will utter these words and let us see what it decodes. For your safety, please remain seated. Look what it has decoded. Okay. So, I will read out for you. For your safety, please remain seated. That is what it has decoded. This is exactly what we had trained this complete model for. Let us proceed now and try to see whether it will decode Welcome to Advanced Internet of Things course. Welcome to Advanced Internet of Things course. So, you see it has decoded, it is completely garbage. So, you can see that it is not really tuned to decode, it is not trained. The training and the testing that has been done for pattern recognition you do testing, and for training you get hold of the model parameters, right. Both have not actually happened for in-flight data. So, this you can now try with another app, you tune it for something else, then you will be able to proceed and then so this is an example of how you can use yourself, you yourself can do this in your by sitting in front of your computers with an internet and a Android phone, you can try this on your all by yourself.